In our last lectures, we reminded ourselves about atomic structure. And all of that was set up so that we could get to the point that we are now, which is to actually delve into how do transitions happen inside atoms that produce spectral radiation. So the next few lectures are going to be developing the concepts that we need to understand how transitions happen, what transitions are allowed or not allowed. So that's one of our strong goals, and what the relative strengths of transitions are for a particular atom. And that's the second of our goals. So to do this, we're going to be treating our, our radiation semi-classically. So that means that we're going to treat the atoms quantum mechanically, and that's why we built up the whole quantum mechanical treatment of atomic structure in the last set of lectures. And we're going to treat the radiation field classically. And in particular, we're going to work with a dipole approximation to the radiation field. Now, before we dive into actually doing this, let me just take a little aside into some history. The Bohr model for the atom, which was one of the first applications of quantum mechanics in describing how atoms actually work, was developed partially to do some of the things that we're doing as part of our atomic spectral lines. It was developed partially to explain why the spectral features observed from given atoms were discrete than particular energy or particular frequencies or wavelengths. And Bohr figured out that in order to explain those, you needed to have discrete energy levels for your electrons. And with the discrete energy levels, you could define the specific wavelengths of light. Now, that worked very well for the specific parts of, say, the hydrogen atom and being able to describe the wavelengths for the series of the hydrogen atom. But it fails on a couple of points. And one point that it fails on is that it doesn't give any way to explain the relative strengths of the different lines for an atom. And that's something that we really want to be able to do when we're doing astrophysical interpretation of spectral lines, because the relative strengths can help us learn a little bit about the medium from which they're coming from. And the second thing that the Bohr model doesn't, it just has to assume and can't necessarily explain because it's not a full quantum mechanical treatment, is that in the Bohr model, because the electrons are orbiting, i.e., accelerating, they should also be radiating. And if they're radiating, they should be losing energy. And so electrons should be continually dropping through energy levels. Now, that clearly doesn't happen, and that's because we need a full quantum mechanical treatment. But that's something else that we can deal with in our semi-classical treatment of radiation. So I'll stop there, but in our next lectures, we'll pick up on semi-classical radiation and work through some of the proofs.